Hello, everyone. We are very excited to be here. Thank you for having us. And welcome to the session, Breaching AWS Accounts Through Shadow Resources. In this session, we will demonstrate you several vulnerabilities that were found on AWS. The most severe of this vulnerability could allow an attacker to inject admin role to another AWS account. So let's start by discussing the most debatable topic on AWS, which is AWS Account ID. Each account has a unique identifier associated with it. This identifier consists from 12 digits. And the most important thing about this identifier is that some treat it as a secret and some don't. And along the history of AWS, we have many different opinions with whether it is a secret or not. Although AWS, in their official documentation, state that this identifier should be shared carefully, they do not consider this as secret. But we, as security practitioners, know that attacker could achieve problematic things only by knowing this account ID. So what is the right answer? Are AWS account ID secrets or not? We hope that by the end of this session, we will have more solid opinion about this. So let us introduce ourselves. My name is Yakir Kotkoda, and here with me are Michael Kaczynski and Ofek Itach. We're all security researchers from Aqua Security Team Nautilus, and we focus on our daily on cloud vulnerabilities, open source vulnerabilities, and more. Let's go over the agenda. We will explain what are shadow resources. Then we will demonstrate several vulnerabilities that we found and an open source tool that we developed during this research in order to find more vulnerability. After this, we will introduce a new technique called bucket monopoly that helped us emphasize the risk of our finding. And we will end our session with some mitigations and recommendations to avoid such a vulnerability, especially on open source projects. Let's discuss how our journey began. While we worked with the AWS Management Console, which is the GUI of AWS, and specifically with the CloudFormation service, we noticed that when a user uploads a template file, AWS, behind the scenes, creates an S3 bucket for the user. Although the user did not explicitly ask the creation of this bucket, this is how the service works by default. We've decided to name this kind of resource that created automatically shadow resources. So let's explain this term. When we refer to shadow resources, we normally refer to resources that generated automatically or semi-automatically by AWS. Most of the time, they spawn without user intervention, and they might go unnoticed by the account owner. And the great example for this is just the S3 bucket that we saw that AWS creates when the user uses the CloudFormation service via the management console. Now let's align another term, which is S3 bucket service. It is one of the first services that exists by AWS. And this service has some spatial uniqueness. For example, bucket names must be globally unique across all the AWS accounts. And for example, if you create a bucket named cool bucket, no one else on AWS will be able to claim this name. It will be available only under your account. So let's set up a gear and talk about our first vulnerability in CloudFormation. First of all, what is CloudFormation? It is an infrastructure as code service by AWS, similar to the Terraform project. A user will usually define a template file that contains other AWS resources. Then the user stores this file locally or in S3 bucket. And then the user needs to define an S3 bucket, a stack that will hold this template file. And when the user will submit the stack, the CloudFormation service deploys the resource that exists on the template file. As we saw before, when the user uses via the management console, behind the scenes, AWS creates an S3 bucket for the user. Now, I want us to focus on the naming pattern of this S3 bucket. It will consist of three parts. First of all, is the prefix of the service, in this case, CF template. It's a constant value that will remain the same across all AWS. Then we have a hash, which is unique per account. And then we have the region. which related to where the user initiates the CloudFormation service. So basically, whenever the user uses the CloudFormation service via the management console, AWS creates an S3 bucket. And then if the user moves to a new region for the first time, AWS creates, CloudFormation creates a new bucket with the same prefix, with the same hash, but with a different region. So we have here a semi-predictable bucket name. So what if an attacker opened this bucket before the user? If an attacker does so, the attacker actually does something that's called S3 bucket name squatting or bucket sniping. You can read a great blog by Oren McKay about this technique. I want us to visualize this. So we have here a user that uses the CloudFormation service on a specific region. And then we have an attacker. And in this case, the attacker creates this semi-predictable bucket name on their account before the user. So whenever the user will try to use the CloudFormation service in this region for the first time, the previously vulnerable CloudFormation service will try to interact with the attacker-claimed bucket. But at first, it will encounter an error. So basically, we have here a way to prevent other users from using the CloudFormation service on a specific region, which can be considered as a DOS scenario. And a DOS scenario is fine, but it isn't enough for a black hat session, so let's escalate it. What if an attacker opened the bucket for a public access? So the reason why we got an error from the CloudFormation service before is because attacker still needs to define some settings on their S3 bucket. First of all, attacker needs to allow public access because it's blocked by default. And then the attacker needs to define a resource-based policy in order to allow cross-account resource access. Here we have a POC of a very permissive bucket policy that allows any principal on AWS to perform any action on the malicious S3 bucket. So whenever the attacker does so, now the CloudFormation service of the victim will succeed interact with the attacker-claimed bucket. So whenever the user uploads a template file, now the template file will be dropped to the attacker S3 claimed bucket. So we have here information disclosure scenario because an attacker can enumerate different secret resources that exist in these services and more. But if an attacker already has access to this file, what if an attacker modifies this template file? So if attacker does so, it's called resource injection on CloudFormation template. It's a great technique that's published by Rhinolab and also credited to Matt Fuller about this technique. And all the idea behind this is some time of check, time of use, default behavior that the CloudFormation service has that allow an attacker or a windows of opportunity to modify template file before the CloudFormation service try to deploy them. So it is possible for attacker to modify the template file and, for example, injecting malicious resources and more. Let's see the full scenario. We have here a user and an attacker. The attacker claimed the S3 bucket that the previously vulnerable service will try to use on a specific region, in this case, EU West 2. So when the user will try to create a stack for the first time, the CloudFormation service uploads this template file to the attacker-claimed bucket. Then we will have a Lambda that will backdoor any file that will be dropped to the attacker S3 bucket. The Lambda will pull the template file and perform a resource injection. In this case, the Lambda of the attacker can inject an admin role that can be assumed by the attacker. Then the Lambda will put this template file, the backdoor template file, on the attacker-claimed bucket. So whenever the user will try to deploy the CloudFormation template, then the CloudFormation service will get the backdoor template file from the attacker S3 bucket and actually create the injected resources. So we have here an admin role that can be assumed by the attacker in external account, which is really a severe scenario. And there are some important points to mention about this. So first of all, in order to inject admin role to another account, the initiator of the CloudFormation service needs to have high privilege. But since that most of the users that uses the CloudFormation service sometimes have high privilege, we can assume this. But even though if they do not have high privilege, it's still possible to modify what exists on the template file. For example, alter EC2 instances and more. And of course, the last thing is the attacker needs to wait for the victim to use the CloudFormation service in this case in a new region for the first time. So let's see a POC. We have the victim that uses the CloudFormation service via the console and uploads the template file. Behind the scenes, the template file already dropped to the attacker claim bucket. The user still needs to define the stack name, give privilege, and more. Then we can see that the template file exists in the attacker S3 bucket, so the attacker can modify it manually or with Lambda. So whenever the user will deploy or submit the stack, we can see we have a new role, an admin role, which has really high privilege. And this role can be assumed by an external account, as we can see in a moment. And then all attacker needs to do is to find the related account ID and assume the role, the admin role on the external account, which is one of the most severe things that we can achieve in the cloud, right?
But Yakir, wait a minute. The technique you showed us is really cool. But before we continue, we should not ignore the elephant in the room. You told us that the bucket name needs to be predictable. But when we look at the bucket name, it's definitely not predictable. We see this hash in the middle. So we knew we had to address this problem. Our first attempt was maybe trying to enumerate and calculate every possible hash. But we quickly realized it's not doable to do the amount of buckets that we should scan. Then we thought, maybe we can reverse the hash, because Yakir showed you before that the bucket name and the account and the hash in the bucket name is actually unique per account. And that means that maybe it's calculated based on the account ID or any other unique identifier. But after many unsuccessful attempts, we turned to open source. We tried to look for a code that shows us maybe how the bucket is created. And we actually stumbled upon this code. And in this code, we can see that the bucket name is randomized. And it gave us the impression that our technique is not going to work, because without the bucket name, we have no way to predict the bucket before the user and use this technique that we managed to remote access an account and create remote admin. But as a great security researchers, we use one of the best security tools that we know, the search tool. We use the Google and GitHub and SourceGraph search tool, and we managed to find over 1,000 buckets, some of them of a really big vendors. So that means that we can attack a couple of vendors. But it's not enough, right? So we kept searching on open source, and we saw this code. And in this code, you can see that in some cases, the bucket name is created by just using the account ID in other services. So we thought to ourselves, maybe instead of using this mysterious hash, this mysterious randomized string, let's just find more vulnerabilities by just using the account ID. Let's find more buckets. So that's exactly what we did. We start exploring every possible bucket. We use the GitHub like before. We use AWS documentation and SDK. We even started crawling and pressing nearly every possible button in AWS. And we created some automations. One of them, called TrailShark, and it's actually open source, and you're all gonna see it. This tool gives you the ability to debug AWS and see the inner API calls within AWS. And it looks like this. On one screen, you need to initialize an API call. Like in this scenario, I'm initiating the API call that Yakir showed you before, the create stack. On the other screen, I'm using Wireshark, which is a convenient tool for security researchers. And in Wireshark, we wrote a plugin that lets you debug AWS like you debug network traffic. And all the API calls that made by the specific API call that we made in the GUI are actually transferred to actually captured by our Wireshark plugin. And that is especially interesting because the API call that we initialize is an undocumented API call. And it's even said by AWS. And when we see the equivalent to that specific API call, we see that it's like 5 or 6 API calls, inner API calls. And one of them is the creation of the bucket. So we used all the technique that we showed you before, and we managed to find hundreds of buckets. And at that point, we knew we have a lot of work to be done because we are not sure which bucket is responsible to what service, because some of them we found in open source search. And we're also not sure if any of those buckets, of those services, is exploitable. So you're wondering probably what is the answer. And the answer for these questions was, we managed to find 5 different vulnerabilities within AWS. Some of them with just using the account ID. So before we start exploiting each vulnerability, let's talk about the common steps for all the vulnerabilities. We need to create a bucket name like Yakir. We need to create a bucket with a predictable name, like you show in Yakir part. We also need to open the bucket to the world, so the victim can communicate with us. And we need something that monitors the bucket, like a Lambda, and it automatically changes the code. Using this setup, we can start exploiting. So let's explore our second vulnerability for today, in AWS Glue. This vulnerability using just the account ID. So what is AWS Glue? AWS Glue is a service for data engineers. And it is used basically most of the time for data manipulations. To trigger the vulnerability, the user needs to create a job. When you do so, an automatic bucket is configured. There, files, scripts will be saved. And this is the exact place that we come to the picture. As I showed you before, we catch the bucket before the user. When the user creates the job, the scripts are actually stored into our buckets. Then we can modify the script using our Lambda. And when the user tries to run the job, he gets the modified script. And voila, we have a remote code execution by just using the account ID on the remote account. So let's talk about the privileges of that vulnerability. So the user configures the job and the role for you. And most of the time, user will configure the default role that you got on the landing page when you are using AWS Glue. And when we are using, and that specific role actually has some pretty strong policies attached to it. And it gives you a lot of enumeration and creation of resources, but it's not our topic for this show. Another cool, interesting anecdote about this vulnerability, it actually gives you an invisible backdoor. And let me explain. When the user tries to view the script that is written by him, by the Glue, he actually sees the original script. And when he runs the script, he actually gets the modified script. This is due to a visual bug in AWS. Now, let's see the full POC that we recorded on February. So as I said before, the user needs to create the job. Here, a victim creates the job, configures the role. When he saves the job, the script is dropped to the attacker bucket. Now let's see the attacker view. So the attacker got the Python script dropped to his bucket. The attacker can modify the script as he wants. In this case, we just wrote pound for the POC purposes. And then when the victim look at the code, as I said before, we got an invisible backdoor. You can see here that he actually sees the original script that he created using the glue visual. And when we look at the output of the script, we actually see that the user has been pwned. Now let's talk about our third vulnerability for today. In EMR Studio, this one is a different little bit, because here we have a cool post-exploitation technique. In this case, it's also using only the account ID. EMR is a service for data scientists, for data consumption. And to trigger the vulnerability, the user needs to create a studio using the EMR Studio. And when he creates a studio, an automatically bucket is configured. And this is exactly where we come to the picture, because we catch the bucket before the user. And when the user creates the studio, he actually dropping the files into our bucket. In this case, he drops Jupyter Notebook files. And we have our Lambda that automatically monitors the bucket. And we automatically change the Jupyter Notebook file. We actually, in Jupyter Notebook, can inject cells. And the cells is automatically parsed by your browser. And what we actually injected is JavaScript in this case. So when the user tries to get his notebook, we will actually get the modified notebook with our stored XSS, and it will be automatically redirected to our fake login page. Now I want you to get Michael. He will talk about more vulnerabilities, and will show you how our technique applies on open source projects.
All right. So thank you, Afik. So nowadays, as you all know, AI and machine learning is the new trend. And you could not miss a chance to talk about this on our lecture. So let's discuss the rest of the vulnerabilities and start with AWS SageMaker. So SageMaker is a tool designed to build, train, and deploy machine learning models. Canvas is part of the SageMaker ecosystem, and it's a very cool drag-and-drop interface. And we discovered that when a user creates a new Canvas instance on a region for the first time, then a bucket is created with the name SageMaker-region-account ID. And the bucket will store files that are utilized by the Canvas service. So let's take a look at the full attack scenario. The attacker needs to claim the bucket before the user. And then when a user opens Canvas, it will create a data set and upload the files. The files will be uploaded on the background to the attacker claimed bucket. And then the attacker could get the data set, and we have data leakage. And if that's not enough, the attacker could also manipulate the data set and then upload it back to the bucket. And we have data manipulation. So the manipulation of the data may lead to inaccurate models. And all of this happens without the user even knowing that something happened on the data set that the models were trained on. Next, we found a vulnerability in CodeStar. So AWS CodeStar is a tool that provides a unified user interface, enabling to easily manage development activities in one place. And CodeStar was deprecated just last week. So in this scenario, the attacker has claimed the bucket before the user. And then the user creates a CodeStar project on a region. Then CodeStar, on the background, tries to create a bucket, and it fails because the bucket already exists. And it returns an error to the user. So this is essentially a denial of service, since an attacker is preventing the user from creating CodeStar on a specific region. And the next vulnerability that we found was on service catalog. We won't elaborate about it right now. It's very similar to the CloudFormation vulnerability, and we are going to publish a blog very soon, and we'll explain this vulnerability on the blog. OK, so on top of the vulnerabilities that we found on AWS, we identified that this attack vector applies to many open source projects as well. So many open source projects create S3 buckets as part of their functionality. And the consequences of the creation changes depending on the logic of the open source project. But some projects are vulnerable and could allow an attacker to gain full access to all of the files in the bucket. So here you can see an example of a project that tries to verify if the bucket exists. And if the bucket does exist, it will only print to the screen that the bucket exists, but it won't exit. So an attacker could claim the bucket, and the creation of the project will succeed. On the next example, you can see a script that checks if a bucket also exists with the AWS S3 ls command. And this check is also wrong, since an attacker could claim the bucket, open it for public access, set permissive policy, and then it will allow the user to list the bucket. So again, the check would be fine, and the creation of the project will continue. OK, so also as part of an investigation, we identified many services that creates buckets with predictable names. And for instance, we identified that AWS Athena created this kind of bucket with the name AWS Athena query results dash account ID dash region. And when we encountered it, Athena did not create this bucket anymore. And nowadays, the bucket is created by the user specification, so we could not find any vulnerability there. So Athena is just an example, but there are many other buckets and many other services that are doing so. All right, so we discussed vulnerabilities in AWS services and open source projects. So now let's explore how we can elevate what we've learned so far to the next level. So we wanted to increase the chances of an unsuspecting victim being compromised. It was important to us to show that this attack vector is not just theoretical, but it's also practical and effective in real-world scenarios. And we are proud to present the technique we called bucket monopoly. So in previous vulnerabilities, we targeted specific regions of other accounts. We could check if a bucket already exists, and if it does not exist, we could claim it before the victim. However, instead of focusing on just one region, we could claim all of the buckets that do not exist yet in all of the possible regions. And it would look like this. So this strategy increases the likelihood of an unsuspecting victim interacting with an attacker on the S3 bucket. But since we have several vulnerable services, let's create all of the buckets in all of the possible services. So whenever the victim will use a service for the first time on a new region, it will be immediately compromised. So let's explain step by step how to successfully perform this kind of attack. So first of all, we must identify predictable bucket names. After finding these buckets, we need to verify that the associated service is indeed vulnerable to this vector. Secondly, we must recognize what is the unique identifier. And the last step, which is the easy one, is to claim all of the buckets across all possible regions. So we showed you several ways how to find these kinds of buckets. We start reconnaissance by looking at the GitHub regexch search. We could also read the AWS documentation and crawl AWS services using tools like TrailShark that Ofek showed you just a few minutes ago. Next, the second step is to understand what is the unique identifier. It might be a random hash, and it will require further investigation. And it could also be an account ID or other kind of public metadata information. If it's a hash, we could search on SourceGraph and GitHub to find leaked hashes and then target them. And if it's an account ID, there are multiple ways to find them. So the first method is, again, to use GitHub and search for specific patterns. We could also leverage the Grey Hat Warfare platform, which search for publicly accessible buckets and extract the account ID out of the bucket. Jerome Brown did this and found nearly 197,000 unique account IDs. We could also extract AWS account ID from access keys. And lastly, there are valuable lists out there of known organizations and vendors that we could just search GitHub and find these lists. And the last step is to monopolize. So attackers utilize their understanding of bucket naming conventions and account IDs to strategically create S3 buckets with predictable names across all regions that these buckets does not exist yet. And by doing so, they position themselves to intercept future interaction of the victim with these kinds of buckets. All right. So let's talk a little bit about the disclosure and timeline. We found those vulnerabilities at the middle of February and immediately reported them to AWS. And AWS immediately started fixing them. And we got a final confirmation that those vulnerabilities were mitigated. So the approach here was consistent. AWS will either add some kind of random string or a number and then create a bucket, or they will ask the user to give a new name to the bucket. Either way, they will ignore the already claimed bucket by an attacker. So to conclude what we've seen up until now, we've identified 6 vulnerabilities in AWS services that might enable an attacker to exploit the organization. We explained how these vulnerabilities occur, and we presented the new attack vector named shadow resource, as well as the technique we call bucket monopoly. While the vulnerabilities in the services that we showed you were mitigated, this attack vector could still be applicable to AWS services in the future, and of course, to many open source projects, as we just showed you. So the first mitigation that we recommend is to prevent an entity that assumes a role from accessing a bucket you do not trust. You can define a scoped resource policy that contains the AWS resource account condition. This approach prevents users and services from accessing and writing data to buckets that are located on accounts that you do not trust. The second mitigation we offer is to run this command to ensure that the bucket used by your services are indeed under your account. Also, the expected bucket owner check is valuable for open source projects as well to safely verify that the buckets that they're trying to interact with or the buckets they're trying to create are not owned by someone else that you do not trust. And lastly, incorporate some kind of a random string or a hash, and then create a bucket, making the bucket name less predictable. So after everything we demonstrated so far, do you still believe account ID is not a secret? Thank you. We have short time for questions.